Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at ECG and we looked at valvular pathology. Before that we looked at Cabrera system and limb leads, and we looked at we had an overview of ECG and the electrical activity. In this video we will look at driven right leg system for ECG, which is essentially a feedback system to minimize noise and improve noise performance. How does this work? Now, we said that the leads of interest are taken from the electrodes that are placed in the right arm, left arm and the left leg. The right leg is not considered for this purpose, and for the purpose of the ECG itself, but we use the right leg for a different purpose, and that purpose is to use it as a feedback system. Right. So, consider this similar to active noise cancellation in headphones. Many of you might be having active noise cancellation headphones. What this does is, when you are hearing some music, it has microphones through which it measures the ambient noise, and then it inverts that noise and actively inputs the inversion of that into your ear, so that the ambient noise you don't hear. This is how noise cancellation works. I mean, check this out. Check out how active noise cancelling headphones work. Due to that, you will not be able to hear anything that is happening around you, only the music or only whatever audio that you are sending through your headphone, only that you will be able to hear. This is how active noise cancellation works. And why is that relevant here? Similar to that, if I can know what are all the various common mode noise that is there in the various leads or various electrodes, then what I can do is I can actively invert that and input that into the right leg to make sure that I cancel that noise. This is the approach towards improving the common mode rejection ratio. Usual common mode rejection ratios are of the order of 80 dB, 90 dB usual. If you include the driven right leg system, sometimes the noise performance CMRR may increase by up to 30 dB, taking it close to 120 dB in some cases. So, that is a lot of dB. 120 dB CMRR is actually a very highly performing system when it comes to noise. It is an excellent noise protection system. So, the idea, what are these common mode noise? Power line noise, for example, noise that is present in the room that you cannot avoid. For example, in an ICU there might be other instruments that might be measuring or providing therapy to the patients, which you cannot remove, but these are common, they are present in the room, these are common to both the electrodes. That is why they are called as common mode noise. These are the common mode interference or the common mode noise. The most common, excuse the pun, the most common of the common mode noise is the power line noise at 50 hertz in India, 60 hertz elsewhere in the US, for example. So, you want to minimize this common mode noise, thus improving the signal quality, and also you want to use this as an opportunity to enhance patient safety in case of electrical leakage. What they used to do, traditional ECG systems connected the patient's right leg directly to the ground. Now, that was not effective in reducing interference. So, the driven right leg system essentially avoids grounding, thus improving safety. because if you ground the patient, it could introduce additional safety concerns. The patient is grounded, that means if there is indeed a potential, then that will actually, then some current will actually flow through the patient, which can be dangerous in some cases. So, it is in particular desirable to not ground the right leg of the patient. So, that is what is achieved in this case. It is not that the patient's right leg is grounded, but rather you provide a sort of a virtual ground. The DRL system replaces the direct grounding with an active feedback loop and minimizes the common mode voltage by providing a sort of a virtual ground. So, what is happening is you take the potential from the left arm and the potential from the right arm, you amplify these through these resistors. These must be matched resistors, and then you have them amplified through these op amps, and then you feed that as the input to the inverting terminal. So, that is where is it fed back? This is fed back to the inverting terminal of this op amp, and then you use a current limiting resistor to ensure that a large current does not flow through the patient. These limitations are, what is the, for DC current must be less than 10 microamps, for AC must be less than 100 microamps. You limit that. Critical to this is the point that the information, the common mode noise from both the left arm and the right arm is fed to the inverting terminal. That is critical, absolutely critical. If the resistors value change slightly between the two op amps of the right arm and the left arm, then the corresponding potentials will change, then they will not be detected as common mode noise. So, that is absolutely, so you need to have matched resistors, that is very critical in your design. So, you measure the common mode voltage on the patient's body, that is measured through two averaging resistors, RAs. These resistors are connected to these two arms, left arm and right arm, and this voltage represents the common mode voltage or the unwanted interference from external sources. Common mode, these are the power lines, are the electromagnetic fields, and then this sensed common mode information or the unwanted interference information is fed into an op amp, in particular to the inverting terminal of the op amp. This op amp inverts and then amplifies the voltage signal. Note that the input voltage range will be plus to minus 5 volts, and you are also having other voltage range. In the previous slide I mentioned about the current, acceptable current range. This is the voltage range for the inverting op amp, right. And then this amplified and inverted signal is fed back into the right leg through the right leg electrode. This feedback essentially creates a negative feedback loop that actively cancels the common mode noise, similar to your noise cancelling headphones. This process greatly reduces the common mode noise or the common mode voltage on the body, thus greatly enhancing signal clarity. It is possible for the patient to have some sort of displacement current, right, caused due to the capacitance that is there between the patient and the surroundings. Importantly, because the patient is not grounded, this displacement current does not flow to the ground, that thus improving patient safety. It is not just reducing noise, but it also improves safety. Instead, it is observed by the op amp's output circuit, thus reducing the interference. What is the worst that could happen? The worst that could happen is that the op amp will go to saturation. That is all, that is what could happen, right. So, what are the benefits of having this system? It essentially reduces common mode noise, in particular the 50-60 hertz noise. Note that 50 hertz is a frequency within which there is which falls in the range of useful frequencies of ECG. ECG signals are from 0 to 100 hertz. That means that if I have 50 hertz, that is, if I use a notch filter to remove 50 hertz, that means that I might also end up removing some of the signal from the ECG, which is not a desirable situation. It improves signal quality, provides a cleaner waveform for better diagnostics. It eliminates the need for direct grounding, and that means there is no need to be physically connected to the ground. That means that it is safer for the patient. It enhances patient safety. Suppose a dangerous voltage for whatever reason appears on the patient due to electrical leakage. For some leakage, a dangerous voltage appears on the patient. What is the worst that could happen? The op amp will saturate and it will essentially disconnect the right leg. But if the patient is keeping the right leg on the ground as per the earlier process, not the current driven right leg process, then what could happen? Then the current will flow through the patient, essentially causing shock to the patient. So, the circuit includes parallel resistances that essentially prevent large currents from flowing in these cases. I already mentioned what are the allowable currents. DC less than 10 microamps, AC less than 100 microamps. However, if the voltage reaches 120 volts, then it can cause damage to the amplifier. That's still the worst that could happen, which is also something that we need to take care of. In terms, when it comes to safety, we need to care for the safety of the patient and also for the safety of the equipment, right. If the voltage reaches 120 volts, then it could cause damage to the amplifier and create risks to the patient. What are the limitations? Well, actually the current designs use not just this, on top of this also use back to back Zener diodes, thus regulating the voltage from at the output of the feedback or the gain amplifier. That is one. The other is sometimes instead of using analog systems, some systems use digital signal processor or FPGA using this DSPs or FPGA, and they have adaptive filtering algorithms implemented using code, and sometimes they may be able to improve the CMRR to values as high as 130 dB. These are the digital implementations. Well, with there is an advantage with the digital implementations. You might think, oh, digital is best, but then the disadvantage is that the lag or the delay in the digital implementation is in the order of milliseconds, whereas in the analog the lag or delay is in the order of microseconds. So, something to keep in mind. It is not that digital is always superior. Depending on the application, you might be interested in using analog sometimes more than digital. Okay. Of course, your op amp characteristics should be that input bias current should be less than 1 nanoamp for your op amp for this driven right leg system, and offset voltage should be, I think, below 50 microvolts. I think so, but do check this. Slew rate of 1 volt per microsecond, and so on and so forth. These are the expected op amp characteristics. There are some op amps that are ready made for that are used for this purpose. You can check those. Many companies offer this kind of op amps that meet these criteria. What are the limitations of the driven right leg system? is not exactly foolproof for high voltage safety. If a high voltage such as 120 volts occurs, the circuit may not fully protect the patient, because the system itself might be compromised and the patient will also become compromised. Sometimes op-amp saturation can lead to system failure. Well, this is the most common situation. If op-amp fails, then if op-amp saturates, sometimes it might cause failure of the system. In extreme cases, the op-amp might not be able to maintain the feedback. Absolutely critical is resistor selection. I already mentioned this. Using incorrect values for RA, RF and RO can reduce efficiency or cause circuit instability. More than that, you need to have matched resistances. That is absolutely critical. You need to have matched resistances. So, with this we come to the end of this video. In this video, we looked at driven right leg system, a form of feedback that is used to improve the signal to noise ratio in the ECG system. With this we end this video, and with this we end the week 6 content. In the next week we will look at the other EXGs. In the next week we will look at EMG, EEG, other. We will spend mostly time on these two. We will spend some time on EOG, ERG and other EXG. Other things less focus. Mostly we will focus on EMG and EEG next week. Okay. So, with this we come to the end of week 6 content. Thank you very much for your attention.